All right, welcome everybody to the Thursday night webinar covering Module 5. I know one thing that everybody probably wants to know is when your test will be graded. Today was actually the first day I was able to get to campus. I did pick up everyone's tests, and I will do my best to have those graded by Saturday or Sunday, and I will post them as soon as they are graded. So you can expect that then. Probably next Tuesday I will scan them and email them back to you and post an answer key to the test so that you can take a look at your graded test and take a look at the answer key and see where you made errors. But our primary focus tonight is Module 5. Module 5 is pretty short, especially compared with some of the previous modules. It's, again, like Modules 3 and 4, it's about comparing individuals and measuring individuals in two variables. But in this case, we measure each individual. One of the two variables are each quantitative, and the two variables are qualitative or categorical rather than quantitative. So let's take a look at this first example on OLI about body image. So the first question that students were asked was, do you feel that you were overweight, underweight, or about right? So they refer to that variable as body image. That is, what do the students think about their body? And so the numbers there next to the students are the student numbers. They're like the sample, the number that person has within the sample, not their age or anything like that. It's not a variable, it's just a label. So there's one variable. So they talk about different questions they might answer, but it might be interesting to divide the students into groups and compare the two different groups on their body image. And the most logical way to do that is to add the variable of gender. Here they're just looking at a table with the different percentages. About 71.3% in the sample of 1,200 felt they were about right, 19.6% overweight, and 9.2% underweight. So they did a bar graph there. But now, like I said, what we're more interested in is comparing two variables. So here now we're recording two variables for each individual, which is their gender and their body image. So the first person in this table was a male who thought he was overweight. The second was a male who thought he was about right. The third was a female who thought she was underweight, and a female who thought she was about right, and then a male who thought she was about right. The raw data is huge to deal with, but we can create, as it says, a table called a two-way table. So here we are, and we have our data here. And what I'm going to do, I think here, well, I think I can highlight within this table. So over here at the row tables, this is the totals for each of the categories for gender. So this 760 that I've highlighted, that means they surveyed 760 females and then 440 males, and of course that adds up to 1,200. And then over here, 855 people in the sample overall felt they were about right. My apologies for my sniffles. My allergies are acting up with the cold weather. 560 females and 295 males felt they were about right. 163 females, 72 males felt they were overweight. 37 females, 73 males felt they were underweight. And then these two 560 and 295 added together give me my 855. And then if I add the three numbers across from female, those will add up to 760. And then add the row totals, those give me 1,200, or add the column totals, and those give me 1,200. All right. So we're really most interested in comparing. Usually we have an explanatory variable and response variable, just like we did before. Here we're probably going to think that gender might affect how people feel about their body, what gender someone is. Okay. All right. So, by the way, they're talking about a few things in here that we'll not worry about at the moment. They're just showing you exactly what I was talking about things, how things add up. So here we go. Is body image related to gender? So what we do now, we don't really care so much about the totals for each of the body image categories. Really, we care about the females, so we go across from females in red, and the males, we go across from the males in blue. Okay? So, as it says right here, there are more females than males. Okay, there are more females than males. So we can't compare the numbers themselves directly to each other. We need to compare the percentages. So that's what they do in these two bullets here. And they compare the percentage of each group who thought they were about right. And it says 73.7% of females felt they were about right, and 67% of males felt they were about right. Fairly close, not a huge difference. We'll see later in the course whether we can say that difference makes us confident about whether all students think they are, whether the percentage of all females and males who feel they're about right is equal or not. But in general, they're fairly close. There's not a huge difference. All right? But when you go to the other categories, so about right was similar, overweight, we've got 21.4% of females and 16.4% of males. So for the males, fewer thought they were overweight. But for females, only 4.9% thought they were overweight, whereas for males, it was 16.6%. So far more of the males thought they were underweight than thought they were overweight. Whereas with the females, the overweight to underweight ratio was much higher. For the males, it was pretty much 50-50 in terms of whether they, who didn't say they were about right, who thought they were overweight versus underweight. And of course, this could be due to some of the gender stereotypes that we have, that men should be big and strong. So there's the guys who are skinny, they feel they're underweight, even though their weight may be healthy. Similarly, the stereotype for women is that they should be lean. Though in the Olympics, thankfully, we see the many images of women who are not particularly lean. The skiers and the speed skaters, etc. But the general stereotype tends to say women should be thinner, and so more women feel they're overweight, regardless of whether they are or are not. And then when we put a side-by-side bar chart, bar graph, and we can see that the distributions are not the same for males and females. And this is really what we're interested in. Take an explanatory variable and look at the different categories of that variable, here males versus females for gender, and then compare them for the categories of the other variable and see if they're similar or not. Okay? All right. So let's see. And it appears, so at the start of this example, we ask the following questions. If we separate our sample by gender and compare the male and female responses, will we find a similar distribution across body image categories, or is there a difference based on gender? Well, it looks pretty much like there is a difference based on gender. Notice, by the way, let's go back up here to where we calculated these percentages. When we divided, what we divided by was the total. So each of the female numbers was divided by the total number of females, and each of the male category numbers was divided by the total number of males. And they called this conditional distribution. These numbers are sometimes called conditional probabilities. These numbers in here, the interior numbers, so those are called conditional probabilities. So what we're saying is, okay, if we restrict it to just the men, what percentage of them are underweight? 16.6%. Or sorry, feel that they're underweight, because it's image, not reality. And if we restrict it to just females, what percentage of them feel they're underweight? 4.9%. So the condition is based on their gender. Um, so here's another example. Is there a relationship between smoking rates and college programs? Sort of like, not exactly majors, but sort of the next category up from majors, sort of your general area. And so it's we're looking at whether or not people smoked in the last 30 days, and then they look at in the different areas. And again, just looking at those raw numbers, it's really hard to tell if there's a group that smokes less or smokes more. So it would make much more sense to convert those to percentages. Now, the first question here says, and I know it's small print, thankfully I'm reading my reading glasses, but it says we want to determine if smoking rates differ across the various college programs, which is the explanatory variable. In this case, that would be the college program. And then they go through there, what percentage of health science students are non-smokers, at least as far as the last 30 days. So to calculate that, you would do 227 divided by 944. You would take the number of health sciences majors who smoked in the last 30 days divided by the total. Oh, non-smokers, sorry, my apologies. 717 out of 944. And in fact, if you look at that and you look at the answer choices, you can see there's only one of these that's possibly correct, because that's way more than half, and this is the only one that's way more than half. 12%, 17%, 22% are all much less than half. 1.32%, that's hardly any. And now this one, it says social science, human services majors, and then here our choices are more likely, less likely than, or equally likely as independent study students to smoke. In order to answer that type of question, we go back up here. Let me bring in my trusty calculator here. I'm just going to use my simple one right now. All right, and I would say, okay, let's take our social science, human services. That's 306 out of 899, and I would do 306 divided by 899. And when I convert that to a percentage, that's about 34% are smokers. And now let's look at the independent study. 134 divided by 394, and about 34% of them as well. So they're pretty close, much equally likely. So we would say equally likely, and then that's our correct answer. And you could go through the whole table. They didn't in this problem, but you could go through the whole table and calculate the percentages all the way down the table, and see which major is most likely or least likely to be smokers. And this is something that's sort of, well, it may be changing, but based on the current implementation of the Affordable Care Act, but the percentages of insured and uninsured based on health insurance in various regions, and if someone is more or less likely to be uninsured based on where they live. These were very large samples, as you can see, 50, 60, 160,000 people. And so our explanatory variable would be the region, and then we would look at the percentages going across rather than down. Where they live might affect whether or not they're uninsured. Whether or not they're uninsured might not impact where they live. Probably doesn't impact where they live. All right. So that's just sort of getting into what the tables are, why we use them. So here we have some majors at a community college and the West Coast, on the West Coast. 12,000 full-time students enrolled at the college. They probably rounded the numbers a little bit. So our two variables are gender and program. So you got art and sciences, arts and science. That's like liberal arts and sciences. That's people who are getting an AA degree to go transfer, is what that first one is. Business and economics. The next ones are all AS type degrees. Business, economics, information technology, health science, graphic design, Culinary arts, we don't happen to have that here at TCC, but some community colleges do have that sort of thing. Even in Florida, I believe we might have one or two. All right, so the question is, we might be interested in, does someone's gender impact their program? In other words, do the programs have different, actually, now that I think about it, let's go through, but you could make an argument either way in this case, but we're probably going to calculate the percentages of males and females in each program is what we would do. So they look at these proportions or probabilities here for each of these, and these are just general probabilities, but the numbers, so here 5802 over 12,000, so there's 5802, there's 12,000. Those are both in the totals column, or the totals column, and then if you divided down here, they would both come from the totals row. It says column totals. It's totals of each column, but this is a row here across the bottom. So those numbers, so then it says what proportion are business and economic students, and that's 7.7%. And basically what we're getting out of that, those numbers are all coming, so there's our 925, there's our 12,000. Those numbers all come from the margin of the table, so we call those marginal proportions, or sometimes marginal probabilities. So when we talk about marginal probabilities, that's what we're talking about. And just to be clear, you notice on the quiz, I don't specifically say marginal probability, and I won't on the test either. I just ask for the probability of something. But just because you might see it in OLI, I'll mention what those things are here. All right, conditional probability is a little bit different. So here you're restricting who you're choosing from. So here it says, if we select, here let me highlight the sentence I'm going to talk about here. If we select a female student at random, what is the probability that she is in the health sciences program? So now we're only looking at female. So now I'm just going to look at this row right here. And I just look at how many are in the health sciences program, which is 421, out of the total number of females, which is over here, 6198. And they came out, as you see down here, 0.07 or about 7%. Another way of asking that, though, is what is the probability that someone is in health sciences given that they are female? So that's another way of asking the same conditional probability. So if you see given, all that means is whatever comes after the word given, or if you write it symbolically after the vertical line, that is all that you're choosing from. So you will not choose from anyone but that. And so you only look at either that row or that column in your table. All right. So here you see that language there. Probability student is in health sciences given that the student is female. Or probability health sciences given female. And then it says you can also put a vertical bar in place of given. So probability health sciences, vertical bar, female. So all of those are different ways of saying the same thing. So let's look at this one here. It says, suppose, and I know this is hard to read, it says, suppose we select a student in the Infotech program at random. What is the probability that the student is male? So now, since it says we're selecting a student in the Infotech, we only look at the Infotech students. So there was 1,058 of them, so that's going to be our denominator. And then we take the males out of that, so 564 out of 1,058. So that would be our answer there. And then probability arts and sciences given female. So again, I'm choosing out of the females. Here's my female, 6198. So a number that are arts and sciences is 4660. So it'd be 4660 out of 6198. And you'll find that that's probably pretty close to 0.75, I believe. So you would do 4660 divided by 6198. So if it says given, whatever comes after the line or whatever comes after the word given is always your denominator. Always your denominator. All right. Go on to the next page. All right. So we have marginal probabilities, which are just there's just probability of one thing, and then now conditional probabilities. Well, there's also one called joint probabilities, and that's the word that uses the word and. So here, this is a joint probability. It says the probability that someone is female in health sciences. Well, we get that from basically taking one cell inside the table and dividing it by the total. So if we go, I'll ignore the example, but female and health sciences, well, there are 421 people who are female and health science majors out of the 12,000. So to calculate this probability right here, you would do 421 out of 12,000. So in this case, when it's female and health sciences, there's no word given, so my denominator is the grand total of everyone. So then you would just do that division. They just carry it out to 2 decimal places. I generally will ask you to do your probabilities to 3 decimal places. Just a 0.1% gives a little bit more to distinguish. Here, 0.05 is only one significant digit, so usually I'll say three decimal places, or if you convert it to percentages, 0.1%, 1 decimal place for the percentages. All right. So those are AND problems, and that's all that's on this page. Those are pretty basic. I don't do much with the risk here, but risk just means probability. So here, if they say, does aspirin lower the risk of having a heart attack, they're really asking the question, do people taking aspirin have a lower probability of having a heart attack? Well, it was 139 out of 11,034, and 239 out of 11,037 for the first one. 239 out of 11,034 for the placebo. So clearly, even without doing the division, since the denominators are almost the same, 139 is much lower than 239. So aspirin does lower the probability of having a heart attack and thus lowers the risk of having a heart attack. So the answer to that question is yes. That was actually a true study. As it says, it has the data up here. So that's true. Here's one. This is a good one because this is one I don't think it's covered in the on-site notes. So let's look at this one right here. All right. So it says talk about the percentage change in risk. Okay. So let's just ignore the calculation on there. So let's just bring it back up to this. And I think I'm going to do this on the other page, on my my writing page. So let me do that. Wait, come up in just a second. All right, here we go. All right, so we hit for the aspirin group, we had 139 out of 11,037, and so that's the, let's see here, let's move that over. So let's write this in probability notation. That's the probability of, oh, that's not very nice. That's the probability they had a heart attack. Move it over more. Let's keep it black. Sorry, black. Given they were taking aspirin. Okay. And now, let's put a parentheses there. And then the probability they had a heart attack given the placebo, they were taking a placebo, that was equal to, let's change to blue just to be consistent, 239 out of 11,034. I believe I'm remembering those correctly. Next, yep. Okay. All right. So then we can say that's about equal to, and let's get our calculator here. So we'll do 139 divided by 11,037. I'm going to carry that out to, I'm going to carry it out to 3, well, yeah. So that's about 0.0126. Okay, for that, and then it's 239 out of 11,034 is about 0.7. All right, so when we talk about the reduction in risk, that's, well, how much lower it was divided by the original risk. So the risk without taking aspirin is this. So this is going to be our denominator. So that's 0.0217. So that's our sort of our baseline. Well, how much lower did we make it? So we're reducing it in risks. The denominator is going to be the higher number. So, and really it doesn't, in some sense, it doesn't matter the order of subtraction because you're just going to convert it into a percentage, whether it's negative or positive. So I'm going to subtract it this way. Okay, so that's equal to 0.00. Let's go ahead and I can probably figure this out, but I'm going to do it with the calculator here. Functions out. So 0.0217 minus 0.0126. That's 0.0091, and then I'll go ahead and divide that by 0.0217. So about 0.419. Okay, so that was 0.0091 over 0.0217, approximately 0.419, which if we talk about reduction of risk, so we would say there was a 42% roughly reduction in risk of a heart attack for the group taking aspirin. All right, so that's the idea behind reduction in risk. There's not a question on that in the quiz. I do believe there is one question on the test about that. So I did want to show you that calculation from scratch rather than just sort of pointing it out on the OLI. All right. So let's see here. And there's that. So the reason why they got 41% versus our 42% is just because of the rounding. This was a smaller number, and so it changes it a little bit, but it's roughly the same. So they rounded more than we did, and so they got a very slightly different answer. On the test, I would not. That's not going to be a something that I would focus on in terms of subtracting off points, unless I specifically told you how many decimal places to use. All right, so percentage reduction in risks, new treatment risk minus reference risk over reference risk. So they got here a negative 0.41, meaning 41% reduction, but it doesn't really matter If you reverse the order of subtraction on top, you just get a 0.009. This would just be 0.41%, 0.41 or 41%, and you would just say it would still be a 41% reduction in risk. All right. Let's see here. Those are just more examples of that. All right, so summarizing, three kinds of probability. Marginal probability, which is just a probability that someone falls into one of the categories for either variable. A conditional probability is where you usually often see the word given, or it'll say if we select, and then it'll give you one of the categories, what's the probability that it's something from the other category, or from the other variable. And then joint is just an and probability, and that is usually a cell from the interior over the grand total. And then here's our reduction in risk. Then again, the order of subtraction is not critically important there. All right. Let's see here. All right. So this is kind of nifty. This is basically using a two-way table, and I don't. There's nothing on the quiz on this. There may be on the checkpoint. There's nothing on the quiz, and there's nothing on the test on this. But it's what's called a hypothetical two-way table, and it's really a neat thing because sometimes it defies what you expect. And there's something coming out about this now. There was just a study recently from Canada that showed that, interestingly, that women who get regular mammograms versus women who do not get regular mammograms, that as they approach middle age from 40 to 50, that there was actually no difference in their deaths from breast cancer. So one interesting thing is that because of the number of false positives in mammograms, that someone who gets a positive mammogram screening actually is, they only have something like a 25% chance of actually having breast cancer, because so many women get screened regardless of whether or not they have a high risk, which is mostly family history of having the disease. So false positives is an interesting thing when you do universal testing. All right, so this one, and we'll do this one on another page as well. So here's some facts. 48% of babies born are female. You may or may not be aware of this, but that's a true thing, that people think it's 50-50, but there's actually a few more males born than females. And one hypothesis might be, there's a couple possible hypotheses, that the Y chromosome is smaller, so maybe the Y chromosome, the sperm with Y chromosome swim a little faster, but that's probably not it. Another is it's nature's way to counteract the fact that that men die younger and boys die than girls, and so if there's more boys at the beginning, then it'll be closer to 50-50 by reproductive years. There's no one knows the real reason necessarily that more boys are born. The proportion of girls who are correctly identified in an ultrasound is 9 out of 10. In other words, what that means is if they say it's a girl, 9 out of 10 times they're right. The proportion of boys correctly identified is 3 out of 4. So that means if it's a boy, then 75% of the time the ultrasound correctly identifies it as a boy. So here's our question. We're going to turn that around. So basically, I'm going to bring these in as snapshots, and those two facts in there, because I want to write them down in terms of conditional probability. So let's do this. Let's take this up. Put this here. I think I got what I wanted to. All right, close anyways, close enough. That stupid line today. All right, so basically what this means is the first number is the probability of a female is probability of female is 0.48. or 48%. Right, the second one, so what we're going to do is we need to we need some sort of way. So female is female. We're going to say UF. No offense to any Florida State fans, means ultrasound female. In other words, the ultrasound identified them as a female. UM. Well, so we've got the wrong two school abbreviations there. That's all right then. Ultrasound male. In other words, the ultrasound identified the unborn baby as a male. All right. So so this is fact one. Probability of a female is 0.48. So the proportion of girls correctly identified is 9 out of 10. Okay. So what that means is the probability that that the ultrasound says it's a female, given that it's a female, is 0.9 or 90%. But the probability that if the ultrasound says it's a male, that if it's a male, that the ultrasound says it's a male is 0.75. Okay. So now what we're going to do is we're going to make what we would call a hypothetical two-way table. That means we're going to make a two-way table based on these numbers, but not based on real data, but based on if there was data that exactly followed those numbers, what would it look like? So we would have, let's say we have gender on the left side, and ultrasound on the top. So the ultrasound could be male or female. The gender could be male or female. And then we have our total down here, and our total over here. And what we're going to do is we're going to use a lot of times what they'll do is use 1,000, and we'll do that. 1,000 is a good number for the grand total, and you actually start at the grand total and you work backwards. So we put 1,000 here. All right, and what we know is 48% of children born are females. So, well, 48% of 1,000, you can do 0.48 times 1,000 is 480, a little less than half, and that leaves 520 males because they have to add to 1,000. Now it says the probability that the ultrasound says it's a male, if it actually is a male. Oh, I've actually got these numbers in the wrong places. My apologies. Let me fix that real quick. I put them in underneath the ultrasound numbers, but they should actually go, the actual genders are here and here on the left. So the female should go here, and then the male should go here. All right. So if it actually is a male, let's get that whole thing out of there. Come on, you. There we go. All right. If it actually is a male, then it's correctly identified 75% of the time. So what I'm going to do is I'm going to take my calculator, and I'm going to calculate 75% of that 520. So I'm going to go 0.75 times 520. And I get 390. Okay. So the ultrasound will say it's a male for 390 out of the 520 hypothetical males, and it'll say it's female for 530. And then for the females, for the 480 females, 90% of them will be correctly identified as a female. Well, it'll be easier to say that 10% of them will not. 10% of the females will be identified through the ultrasound as a male. That's 48. And then subtracting 48, I get 432 will be identified as female. That's the 90%. You can multiply 480 by 0.9. Now, adding down, we'll get the totals down here. I get 562, and I get 438. These should add to 1,000, and they do. All right. So now my question is, in this problem, I don't need to go back to it. if the ultrasound says it's a female, what's the probability that it's correct? And if the ultrasound says it's a male, what's the probability that it's correct? In other words, what's the probability of a male given that the ultrasound says it's a male? And what's the probability that it's a female given that the ultrasound says it's a female? All right, well, remember, the given is all you look at. So here's the ultrasound. So I'm only, for this first one, I'm only going to look at the ones where the ultrasound identified it as a male, because that's what I'm given. All right, so it's correctly identified for 390 out of the 438 where the ultrasound says it's a male. Then for the females, it's correctly identified for 432. For 432 out of the 562. So now we'll take our calculators. Stop that. Give myself a little more room there. All right, so I take my calculator and I will do for the ultrasound male, I'll do 390 divided by 438. And I get 89%. So about 89%. And then for the females, I get 432 out of 562. And I get about 77%, 76.9% rounded. But I'll round it to 77%, that's fine. So it's kind of interesting that even though the ultrasound is better at correctly identifying females, if the ultrasound says it's a female, it's more likely to be wrong. Why the heck did that happen? Well, it happened because the misidentified males, the 25% of males, 75% are correctly identified. The 25% who are incorrectly identified are clearly identified as females. Again, for those of you who are not familiar with why that might be, why the males are harder to accurately identify through an ultrasound, the answer is that it's because the male male baby might be sitting in a certain way to hide its penis, which is the way they identify it, and so that's the identifying factor. So if they miss that, they're going to say it's a female. Well, for the females, that's pretty accurate, but for the males, 25% of the time they don't see what they're looking for, and so they misidentify it. What that means, they identify it as females. So more of the ones identified as females by the ultrasound are incorrect. I think that the numbers are more accurate than they used to be, but I don't know. This is from a statistics book in 2001. I don't know when and this is an assumption. It says assume the following facts are known. I don't know if how correct those numbers are. And then they walk through exactly what we did. All right. And you can read more about it in the OLI. And then the next page is our summary and our checkpoint. Let's go back and let's talk about one other thing, because in Module 5, it doesn't talk about the, let me pick a page that I think will work. Well, let's just go back to the very first page. They don't talk about OR probabilities. They don't talk about that until Module 6. But I do in the on-site notes. So in order to answer the question in the on the quiz about OR, you need to go through the on-site notes. But I'll also do it here in the webinar. So let's take a look at, here's the two-way table. And you'll see that we have females, males, about right, overweight, underweight. So let's ask an OR question about this. We can even go back to our I think I pulled the data in today. I don't know. Oops, I didn't mean to do that. Oh, I didn't put it in the table. I thought I did. Oh no, I copied that other part in. All right. But let's suppose I wanted to calculate the probability that someone was female, or let's say thought they were overweight. Okay. Well, or means it could be either one. Means if someone is female, we'd count them. If someone thought they were overweight, we'd count them. So you might think what we're going to do is we're going to add the females plus, I'm going to write overweight, but that's body image, not actuality. All right. And we'll divide that by the total. So if I go back and let's see, there was 760 females, 235 people who thought they were overweight, so we do 760 plus 235, and I think there was 1,200 total. But if I add 760 and 235 is these numbers, the 163 and 72 added together, and 760 is these numbers added together. What happens is I add the 163 twice. So I actually need to subtract off minus the ones who are female and think they are overweight. So that's minus, I say 163, yeah, minus 163. And I'm not going to go through the calculation, but you just add and subtract from the top and divide by the bottom. So for an or, you add the two things, but then you subtract off where they overlap. And that's all there is to or. So it's just not in OLI, it's only in the on-site notes. So you do need to, I always expect when I write those quizzes that you're not looking at one or the other by itself, but that you're looking at both. So if you don't see how to do a particular type of problem, maybe you need to look a little more. All right? So that pretty much wraps up this module, module 5. Oh, sorry, using the aspirin. I don't know why I didn't hear your question. Gypsy, my apologies. That's weird. I heard when Jenny joined, but I didn't hear the noise when you asked your question. I'll double check my preferences. Do either of the two of you have any other questions other than the one Gypsy asked and then figured it out? This module's not too bad, so Jenny's got it. Good. So hopefully, it'll work out for people. It's a good module to kind of get back into things. All right, good deal, Gypsy. It's a good module to get back into things after the first test, because it's not too overwhelming. I think the first half of Module 6 is not too bad either. The second half of Module 6 gets a little tougher for some students, but we'll do our best to get you through it. Well, if there are no other questions, then we will wrap up our webinar there, and I will be on Monday of next week in case anybody has any last-minute questions. That might be a quieter one, hopefully. It's always good. It just means people have most of the answers already to what they're curious about. But if you do have any questions, please show up on Monday, or of course ask on Piazza, or send me an email. Have a good night and a good weekend, and a happy Valentine's Day.